So the plan is that we will begin chapter 10 tonight, talk about nonlinear functions and properties of all kinds of functions. And then we'll talk specifically about quadratic functions, mostly how to use the calculator to help you graph them and find information about them. And then we will do rational, exponential, and logarithmic functions on Monday. Your test is not next Monday night. I've made up the test already and I put it in my math lab because my math lab actually, oddly enough, doesn't do a bad job of grading things in chapter 10. It does a terrible job in chapter 5 because of all their rounding issues. But in chapter 10 it does a good job, and a lot of the tests that I'm giving you, some of it is actually multiple choice homework and multiple choice questions on the test. But I promise you there is nothing on the test in my math lab that you won't see doing the homework in my math lab. And I've edited the homework in my math lab down to where, while there's probably a lot of problems still, it looks like to you, a lot of them, like I said, are multiple choice problems. You're going to say graph this equation and you'll graph it on your calculator and look, see which one it is. So it's not going to be the kind of thing where it's going to take you hours to do your My Math Lab homework. And I've already got it up and got the due dates. I've also got the test up. I will give you the code for the test next Monday night when we finish. And you will have from Monday night after class until, I think I gave Saturday night, till 11:59 Saturday night, to pick your window to do the test. You don't have that whole time to do it, but you'll have 2.5 hours from the time you start till the time you finish. And then if anything happens, you can just let me know, you know, like my computer crashed right in the middle of the test, and we'll figure something out. Because that has happened, although not normally, but I mean, it can happen. You know, you can have a power outage. So we'll take care of that. So, chapter 10, nonlinear functions. First thing we're going to talk about in 10.1 is properties of those functions. And what we've got in this picture, and this picture is duplicated in your notes, is a picture of a graph that shows the price of gold from 1970 to 2015. And that's definitely something of relevance to a business major. So this graph is a function, as you're going to learn, but it is not a linear function. You can tell it's not linear because it rises and falls, and it doesn't rise and fall in a straight line. Now, in the long run, most things actually look more like this than they do straight lines. Most functions that we'll use in business don't actually even approximate a linear function. Now, you could approximate the price of gold, for example, from 2005 to 2015 with a relatively close linear function, or maybe from, oh, I don't know, maybe, I don't think I'd want to try it from 70 to 80 because there's too many dips and curves. So the only place that it's close to being linear is from about 2000, looks like 12 or 13. From maybe about 2000 to 2012 or 13, it's relatively straight. But beyond that, it's not a linear function. We could use the graph to answer some questions, and one of the things that we're going to do is talk about a graph and answer some questions from it of a different kind of information. But the first thing I want to do is give you some definitions, and these definitions are in your notes. A function is a rule. It can be an equation, it can be a table, it can be a graph, it can be words, it can even just be a picture. But it's a rule of some kind that assigns each element from one set to exactly one and only one unique element in a different set. Now that's math language for saying, since most of the time we deal with y is equal to something times x, for every single x value in a graph, there will only be one y value. So we're talking about the set of all x values. What a function does is for any x that you plug into the function, whether it's an equation or a graph or whatever, you'll only get one y value. And the x values and y values are so special, they have their own name. And the name of these is domain and range. The domain is the set of all the input variables, or the x variables. And the range is all of the outputs, or the dependent variables, that come out when you plug in the x values. Now, all of that's just math language. It doesn't really tell you anything practical, so we're going to look at some examples. And I think until I need the calculator, I'll make that a little bit bigger so we can see better. So the first example that we've got here is the Dow Jones Industrial Average. And since I've got the PowerPoint and we can see it better on the PowerPoint, I'm actually going to bring up the PowerPoint for this part. So here we've got a graph of the Dow Jones Industrial Average. Pull the screen down a little more so we can see the bottom axis. And just like we saw with the price of gold, the Dow goes up and down and up and down. Now, you could approximate the Dow over the course of the year with a linear function. Because, you know, you could probably, if you just picked every day's value and didn't connect them all up with a straight line, you notice that you do have a relatively constant increase in the Dow over the course of that year. But it would only be an approximation. What this graph gives us is the exact value of every single day in the year for 1 year of the Dow Jones Industrial, and this was in 2013. Now, the questions that we want to ask about this graph, and these are in your notes, is f of t a linear function? And obviously the answer is no. No, because it increases and decreases throughout the year, and if it was a linear function, it would constantly increase or constantly decrease and never deviate from that. So we could fit a straight line to it. It is a nonlinear function, however. It has an independent variable. In this case, the independent variable is the number of days since January 1st, 2013. And the range is the closing average for the Dow on that particular day. So the domain and range of this particular function goes from t equals 0, where 0, as we said, corresponds to January 1st, 2013, to t equals 365, which would be when it closes on December 31st, 2013. And there's 365 different values in there because there's a unique value for each day. The range of the function, on the other hand, if you look here, it appears that on day 0 that the beginning value of the Dow was about 13,100. Because here's your 13,000, and the next one up is 14,000, and right there is where the graph actually begins. And for the first day, actually, the price didn't change because the Dow Jones is closed on January 1st, so it would stay constant for that one day, but then after that, it began to increase. And when it finally got to December 31st, it looks like it's all the way up here at over 16,000. Maybe a good estimate for that would be 16,600, 16,500. If we don't have the data, it's hard to tell. We don't have the table of values. But that would be the range from 13,100 to 16,500 or 16,600. So the range is the Y values, and the domain is the X values, which is the number of days in the year. And of course, like this is February 1st, so it's day 32. And then the next part asks us to estimate f of 14. Well, that would be January 14th, basically, because it's the 14th day after day 0, which is January 1. And if you look at about the 14th day, since this is 32, then probably the 14th day is right about there, if I were guessing. And if that's the 14th day, it looks like maybe it's roughly 15,000. That would be not a bad guess. But the best we could do with a graph is guess, because the graph is not accurate. What did I?
No, I was just wondering how is it 15,000 on the 14th day?
Oh wait, no, on the 14th. No, it isn't 15,000. It's more like 13.5, because here this is probably about the 14th day, and if I drew a vertical line right there, that's probably pretty close to about halfway between 13,000 and 14,000. So 13,500. Okay, the domain is the numbers on your x-axis, which corresponds to the number of days in the year 2013. So your domain is from 0, which is January 1st, 2013, to 365, which is December 31st. The range, on the other hand, is the closing averages. And those range from, the graph actually, you can't see this one on the PowerPoint, but it actually starts right about here, which is around 13,100. And then if you go all the way up to the highest value it ever gets and read back across, it appears the highest value is about midway between 16,000 and 17,000, which makes it 16,500. So your range is from 13,100 to 16,500.
Can you just write that as an ordered pair?
You just write it as an ordered pair, and actually you put it in square brackets instead of parentheses, because it's not an ordered pair in the sense that we're graphing it. It's a beginning and an end. And the reason you use the square brackets is because it includes the value from 13,100 and 16,500 or 16,600. I'm not picky about whether you use parentheses or square brackets, though. The notation's not what's important, it's the idea. What if we wanted to know at what point or on what day or days, maybe, that the Dow was around 14,250? Now that gets a little more interesting. 14,250, well there's 14,000, there's 15,000. That means right there is probably pretty close to 14,500, and then halfway between here and 14,000 will be 14,250. So if we were to draw a line, if we had a ruler and drew a line from here straight across, we should be able to estimate about when that happened. And it looks like that probably happened pretty close to the 1st of March, wouldn't you say? Does that look about right? About 60 days in? Now, we don't know if it was exactly the 1st of March without numbers, but we could get a good estimation. Now, if you have the actual data, which is what we're going to look at next, then you're going to see that the 1st of March was not exactly when that happened. So let's look at the table, which is the next slide. And this is the table of the first few days. And we see that in the first few days, that on day 7, it basically had increased up to about 13,384.29. Okay? Now, if we could continue the table, then we would be better able to tell, and maybe I'll be better able to tell with my paper copy of this table here. If I can get it big enough. So we need 14,250, which is roughly right about there. And if I go straight down, you can see that it isn't right at March 1st. It's a few days after. You still can't tell when it's March 3rd or 4th or 5th, but if we had that continued table of data, on March the 5th, it actually turned out to be 14,250. That was day 64. Okay? But the best we can do with the graph is an approximation. Now, if we were to be asked what is f of 6.5, even with the table we don't know. Because there is no closing average 6.5 days in. So there are some numbers in this particular function that don't make sense. We can only have numbers from 0 to 365, and it has to be whole numbers. You can't use a part of a day because the Dow only has a closing average once a day, and that's when trading stops for the day. So that's the idea that, you know, just because it appears that you can connect everything up at every single day and hour and minute has a value, in this particular case it really doesn't. Now here's another example, and the question here is, which of these are functions? So here is a set of numbers, x. Those numbers are 7, 9, 16, 43, and 28. And they're mapped to another set of numbers, 60, 12, 19, and 27. Remember that the definition of a function is a function assigns each value in x, the domain, this is your domain, to one value in the range. So does this appear to be a function, or do you see something that causes you to be suspicious? Okay, yeah, 28's a problem, because 28, sometimes it likes to partner up with 19. But then a little later it changes its mind and says, no, I think I'll be 27. I think I'll partner with 27. That's the reason that this is not a function. Be sure that you understand that it's perfectly okay that both 9 and 7 went to 12. Because those are different domain values. They can both have the same partner in the range. So that was all right. It's even okay that 28 and 43 both partner with 19. The real problem is that 28 is trying to partner with two different range values. So this is not a function. So then we'll look at some other examples. What about the x squared key on a calculator? Can you put in the same number and get two different answers? You type in a number, it squares that number, gives you the answer. In the process of squaring it, is it ever going to be possible it gives you two different answers? No. So if this is the function that operates on x, and you feed it x is 4, it says, okay, 4 squared is 16. It doesn't come back and say, well, okay, sometimes I'm 16, sometimes I'm negative 16. It just says, no, it's 16, okay? Same thing if you let x be 2, it says 2 squared is 4, and it never comes back and says, no, but I've changed my mind, that's 5. So that is a function. And that's because for every number you put into the calculator, there's only one answer that's going to come out, and it's never going to change. What about this table? Is this a function?
No,
Why not?
because there's more than one part attached to the same x value.
Yeah, we've got the same x value here twice. When x is 1, sometimes it wants to be 3 in the range, and then other times it partners with negative 3. Can't do that. That's not allowed. Same thing with 2. 2 can't seem to make up its mind. Can't decide if it's going to aim at 5 or negative 5. And the same thing with 3. 3 can't decide if its partner is going to be 8 or negative 8. So that's not a function either. Now these sound a lot alike, but you have to think carefully about what they're actually asking. The first one is a set of ordered pairs, where the first element in the ordered pair is the children. And the second elements are the children's birth mother. Is that a function?
Yes.
That's true, but is the mom the domain of the range? She's the range, okay? So every child has one unique birth mother, okay? A child cannot be born of 2 different mothers, only of one. It has one unique mother, okay? Flip that around, because this one is a function. This one flips it around. The first element is the children's mother, and the second element is the children. So now the children are the range. Can a mother have more than one child? Yes. So this is not a function. Now, if you can think of functions in terms of things like this rather than numbers, it helps you to understand what a function truly is, and you don't get mixed up about the x's and the y's. Okay? Remember, the domain can only have one partnering range value. Still talking about functions. This is a graph of 11 minus 4x squared. Is that a function? What's the domain of the function? Assuming that it continues the behavior that it has here and keeps on going down and out on both sides. Okay, its domain is negative infinity to infinity. Is there a limit to its range? What's the highest value in its range? It's, looks like it's,
Well, the X's are legal like ones, but I'm pretty sure it goes by fives and one.
I'm pretty sure it is too. So that must be 5, looks like. Okay? So if that's the case, and if it's not exactly 5, whatever that is, that's the top of its range. It does continue on downward as this domain goes downward. It continues to negative infinity. In fact, that's actually where it starts, is at negative infinity. So its range starts at, whoops, negative infinity, but it goes up to, and looks like it goes up to 10. Now, in truth, it actually goes up to 11. Okay? The reason that we know that is because on that axis, the value of x, the domain value, is 0. And if we know that x is equal to 0, then the range value y is 11 minus 4 times 0 squared. And 4 times 0 squared is 4 times 0, which is 0, and that means y is actually equal to 11. But if I were judging solely by the graph and not having the equation, then I would have said about 10, and that's okay. It depends on what you got. So given this information, the question is this a function? Is there any possibility that you will put in an x number and get out 2 different y answers? No. Because when you put that number in and square it, and it squares that number, it's always going to get the same result for that particular number, right? And then it's going to multiply that particular result by 4 and subtract it from 11. So there's no way that it's ever going to have a different range value. So yes, it's a function. So that one is a function. Now we're going to talk a little bit later about a way to tell quickly with a graph whether it's a function or not. So here's another graph. Is that a function? This is the graph of x equals y squared. If I plug in 1, x is equal to 1, what could y be? It could be 1 or it could be negative 1. If I choose x to be 1, there's negative 1. If I choose it to be 1, sometimes it's positive 1. Same thing happens here, and they're actually showing you this. 4 is paired up with negative 2. But it also pairs up with positive 2. So this is definitely not a function. And I can be really specific. All of the domain values except 0 have 2 possible y values. The only one that's not an issue is 0, because there is one single point, 0, 0 on this graph. But as soon as you move from 0, 0, it automatically, quickly has 2 values for every single input that you put in there. Is this a function? Mm-hmm. What are the domain values? All of them. There's only one range value, but the domain values, it says it goes on to negative infinity and positive infinity. So your domain is negative infinity to infinity, but you have one single range value. Just one. Now the fact that x, every single one of them partners with that one range doesn't matter, because negative 2 partners with 7. 3 partners with 7. Negative 10 partners with 7. 8 partners with 7. But they all have a partner. It's okay if that partner is the same for all of them. So yes, this is a function.
Why is it just 7 instead of 7 to negative infinity?
Because the only y value is 7. Every single one of these. Negative 10, 7. Negative 4, 7. 8, 7. There's no other number in the range except 7. Okay? Okay, here we've got another graph. Is it a function? Yeah.
Yes.
Because there is no place on that graph where an x value doesn't have one single unique partner. So yes, it's a function. What if I ask you what was its domain? You have to think carefully. That's right, because its domain doesn't continue on to negative infinity. It stops right there, or it starts right there, and it ends right there. So your domain values are your x values from negative 1, and since that's a closed circle, it actually includes negative 1, which is what the square bracket means, and goes up to and includes the number 4. So that's its domain. That's why even though they look like ordered pairs, they really aren't. It's just showing you the interval. It's actually called an interval. Now the range, on the other hand, is also limited. How low is the lowest value that this goes on the y-axis? 0, because that's where the bottom is. The bottom's right there, which that's 0. How high does it go? It goes up to 3. So your range then is from 0 to 3. So remember, when you're looking at domain, you're looking to values on your x-axis, but when you're looking for your range, it's values on your y-axis. Now the agreement that we're going to make on domains and ranges, and this, again, I'm going to switch back to the PowerPoint because sometimes you can see it better. We're not there yet. There we are. Unless otherwise stated, assume the domain of functions is defined by an equation as the greatest subset of real numbers that are meaningful replacements for the independent variable. There's some more of that math language. Realistically, what does that mean? Well, in math, in arithmetic, there are two things we cannot ever do. We're not allowed to do it if we're staying in the set of real numbers. And the first thing we're not allowed to do, this is one of the two very important commandments in algebra, thou shalt not divide by zero, ever. You cannot have a zero in a denominator. Division by zero is not allowed. So there's concern number one. Concern number two, thou shalt not ever take even or square roots of negative numbers, because there is no number that you can multiply itself times the opposite of itself and get a positive answer. Okay? If you have a negative number under a radical, you don't have any twins to take out and still be a real number. No real number can multiply itself times its opposite and get a positive answer, and you have to take square roots of positive numbers. So we worry about those two things. So with that in mind, we'll find the domain and range of these. F of x equals x squared. F of x takes whatever you give it and multiplies it by itself and then hands you back the result. Is it ever going to divide by zero? No. Are you ever going to take a square root of a negative number in that function? Does it take square roots? Does f of x equals x squared take a square root? What does it do? What is its only job? What's the only thing it knows how to do? Square. It doesn't know how to take square roots. So given that that's its only job, its domain and also its range are all real numbers. And you can write it that way, or you can write it as negative infinity to infinity. So for this one, you can say it either way that you want to. All real numbers or negative infinity to infinity means the same thing. Y equals x squared, which looks an awful lot like the first one. But the domain is specified to only be -2, -1, 0, 1, 2. Now they gave you the domain. What's its range? Question already done. Question already done.
I'm done.
Okay.
Yeah.
So we've been given the domain. What happens to -2 when you plug it into the equation? You get, when you square -2, you get +4, right? So the range, first value is going to be +4. What happens if you square -1? What's -1 times -1? +1. What happens if you square 0? You get 0. What happens when you square 1? You get 1, but it's already in there. Do we need to write it down again? No. What happens if you square 2? It's already in there too. So actually, wrong one. The range is only 3 numbers, 4, 1, and 0. That's all the function can ever be, as long as this is all you ever let it have to eat. Okay? If this is the only thing you feed it, this is the only thing it can give you back. You don't get to put in -1/2 because that's not in the domain. You don't get to put in 5 because that's not in the domain. That's the only three numbers you can get out when you put a number in. And that's the way to think of it. So with that in mind, let's look at y equals 6 minus x. What is its job? What does it do? What does y do? Takes the square root of something. Okay, so there's a red flag. It takes a square root. That could be a problem. It takes the number 6 and subtracts whatever you give it from 6. And then it tries to take the square root of the result. Can x be 6? Let's think about numbers here. Can x be 6? What's 6 minus 6? 0. Can you take square root of 0? Yeah, square root of 0 is 0, because 0 times 0 is 0. Okay? So, yeah, we can do that. What about if x is 3? It's the square root of 6 minus 3. Square root of 3. Doesn't have to come out even. You can still do it. So yeah, that's a check mark. What about x is equal to 0? Yeah. 6 minus 0 is 6, and you can take square root of 6. What if x is negative 2? 6 minus negative 2 is 8. And you can take the square root of 8. Okay, let's go over here to the other end. What about if x is 7? Is that a problem? Yeah. What if it's 6.1? Still get a negative 0.1 under a radical. So the domain of the function includes -6, but nothing above it. And it goes all the way down to -infinity. So since we always write the domain from smallest to largest, its domain is from -infinity up to and including 6. What about its range? Is it 0 to infinity? There's an easy way to figure out what the range is. That's why I have the calculator handy. We'll start out with 0 to 10. Well, let's go down to -10. Okay? Now, you can't tell it from there. But you can from here. does that graph ever go below 0? No, because when it starts at 6, then the value is 0, the square root of 0 is 0. Now, if you pick numbers that are less than 6, notice that you're taking the square root of larger and larger and larger numbers, which means that its top end is going to continue to go up forever, but it's never going to go below 0. So that tells you that its range is from 0 to infinity, and it includes 0. Because at 6, it's going to be 0. So if you have a hard time telling what the range of something is, you can graph it and look at it and say, okay, is there a place that doesn't go below? Is there some place that doesn't go above? Now, without graphing it on the calculator, what about f of x equals 2x squared plus 5x minus 12? And when you think about the domain for this one, think about the domain for that one. Because even though this one does more work, its first job is the same thing as that one's first job. Its first job is to take a number and square it, and then multiply that by 2, and then take the same number and multiply it by 5 and add it to the first answer, and then subtract 12 from the result. So is it ever dividing by 0? No, it doesn't divide as part of its job. Does it take any square roots? No. So it doesn't. Square root is part of its job. Therefore, its domain is all real numbers. The question is that also its range? And to think about its range, you've got to remember what its y values are. Now, if I plug in x is equal to 0, what's the value of f of x, or f of 0? It's negative 12. Now, anything else I plug in, it's going to take that number and square it, which makes it bigger. Even if it's negative, it makes it bigger. And then it's going to multiply that by 2, which makes it bigger. Then it's going to add 5 times that number, which again makes that even bigger. And then finally subtracts 12. So it's not going to ever go below negative 12. Okay? So if you think through it, then you know that the range for this function begins at negative 12, and it only increases from there. And again, you can use your graphing calculator and verify that. We go to the y equals screen and plug in 2x squared plus 5x minus 12. Just go from a window from negative 10 to 10. We're not going to see, we'll probably see it. I'm going to let it set the y. So zoom 0. Well, what did I make you mad about? Oh, it doesn't want the parentheses. Sorry about that. So I'm going to let it pick a window first. And notice that it does go below the x-axis. But it doesn't go very much below the x-axis. It goes down to negative 15. So if I let that go down to negative 25 and go up to just 100, it's not hard to see that it bottoms out right there. Okay? And if you want to know why does it bottom out there, notice that this is its y-intercept. There was a time it went a little further down. The other thing you can look at is your table. Notice at negative 1 it went to 15, negative 2 it went to 14, and then it starts coming back up again. So my guess is it doesn't go down to negative 12, even though that was a good place to get in the ballpark. It actually goes down as far as negative 15, which we would not have figured out without either a table or the calculator. Drawing a graph is the only way.
And that's -15.
That's a negative 15. And the reason is because if you go to, just for example, -1 squared is 1. So 2 times 1 is 2. 2 minus 5 minus 12 is -15. There are a few numbers on either side of 0 that actually do drop it down a little before it raises it back up. So that example is in here to convince you before you decide on a range for a graph, put it in your calculator and look and see where it bottoms out. Now, if you wanted to know exactly where it bottomed out without having to go to your table, you can also go, and we're going to use this in here in the next section too, you can also go down and find the minimum or maximum. In this case, it's a minimum, and if I want to know what the minimum value is, I work it just like I do the x-intercepts that I showed you how to find before. You move to the left of it, press enter, move to the right of it, press enter, and then tell it to find it. And it says that bottom value, it says it's negative 15.125, so that's the exact value. Okay, and that's when x is negative 1.25. So if I show you the graph, you can use the graph to estimate it. If I give you the equation and you graph it, you can always find the absolute minimum. Okay? Now, the more important one I want to look at this time, though, is f of x equals 2 over the quantity x squared minus 9. So what does f of x do? What is its job? It takes a number and squares it, subtracts 9 from it, and then takes that result and divides it into 2. The squaring part, no problem. Subtracting 9, maybe a problem, because its next job is to divide. One of the things you can't do is divide by what? 0. So that means this cannot be allowed to be 0. Is there anything that would make it 0?
3.
3 and negative 3. Because 3 squared minus 9 is equal to 0. And negative 3 squared minus 9 is also equal to 0. Don't forget to put parentheses around that when you're checking that out. So x can't be either one of those two. Now, I don't have any issue with it, but because sometimes my math lab will ask you to give it as an interval, in words, you can say it that way. X can have any real number value except 3 or negative 3. And that's lots easier to understand. But in my math lab's brain, it wants you to tell it what X can be, not what X can't be. So the way you have to think of this, and again, I'm going to draw you a number line to help you figure this out. Any real number goes from negative infinity to infinity. The only numbers we have a problem with are negative 3 and positive 3. We have to leave those out. which you can think of as being a hole in the number line. That means this interval goes from negative infinity to 3, but it doesn't include 3. This interval goes from 3, not including 3, to positive infinity. And the interval in between goes from negative 3 to 3, and again, it doesn't include either one. And the symbol that they use to go between them is a U, which means and. Actually, it means or, but that's the symbol they'll use. So its domain is negative infinity to 3, or negative 3 to 3, or 3 to infinity. But by putting in parentheses, we've left out the 3 and the negative 3. Okay? So when you're in my math lab, if you need to, come back and review this. The number line makes it easier to figure out what you're doing. So now we've got one more. Find the domain and range from the graphic. But it doesn't have a line. It just has points. So what cardinal points gives you domain? The x-axis. Okay. So its domain is negative 2 and negative 1 and 0 and 1 and 2, which means its range values, and we've actually done this, I just drew a picture of it. Its range values are 4 and 1 and 0, because they're repeated on the other side, so you don't need to write them down again. Next thing we're going to do is called evaluating functions. The function that we're given is negative x squared plus 4x minus 5. And we're going to find g of 3, g of a, g of x plus h, and g of 2 over r, and then try to figure out the values of g when g of x is equal to negative 12. So let's start out with part A. G of 3. This is g of x. That means every place that you see x, you put in a 3. So negative 3 squared, remember that squared only goes to the 3, not to the negative sign, is negative 9. 4 plus 3 is 12, minus 5. Negative 9 plus 12 is 3, and 3 minus 5 is negative 2. You could do that one easily on the calculator. And in fact, since we're going to do something else with it in a little while, I'll put it in at y equals negative x squared plus 4x minus 5. And there's 2 or 3 ways to do this. I'm going to show you on the calculator 2 different ways. One of them is to enter your function in at y1. So you put your function in. Then you quit. To go to your arithmetic screen. Then you press your vars button. And your right arrow over to the Y vars button. And you choose function. And you choose Y1. And you press enter. Oh wait, you don't press enter, you choose Y1. We need to give it a value. So in parentheses after Y1, you put the number you want to evaluate it at. And since we want 3, we type a 3 and press enter, and it says the answer is -2. No arithmetic needed. The other way you could have done it was you go to your table and set it up to let you ask for a value. Leave the other one on auto. And then hit second graph. And then you can ask it for whatever numbers you want. So if you've got a whole bunch of them, you probably want to use the table. And the one we want to ask for is 3, so we ask it for 3, and it says it's -2. Now, if it had asked us to build a table of values to graph the function, we could have used that to get a whole bunch of points to draw your function, to draw your graph. So there's the calculator help. And we're also going to use it on part E, by the way. What about G of A? G of A says the same thing G of 3 does, except you're plugging in A. So every place you see X, you put an A. So G of A is -A squared plus 4A minus 5. We're going to do the same thing with G of X plus H. We're going to plug in X plus H in place of X. But then we have to actually simplify this. So X plus H squared is X plus H times X plus H minus 4 times X plus H. Yes, plus 4. Thank you. And then subtract 5. So X times X is X squared. X times H is XH. X times H is XH. And H times H is H squared. The negative sign is in front of all of that. Plus 4 times X plus H. Minus 5. This says change all the signs of everything inside. Negative X squared. And since I've got 2 of these, it would be easier to combine those and make just 1 out of it. So that's 2XH with a negative makes it 2XH. Minus H squared. Plus 4 times X is 4X. And 4 times H is 4h minus 5. So not only do you need to know that you plug it in, but you need to be able to do the algebra necessary to actually write out all the terms. That will be very important next semester in the very first chapter of calculus, because we're going to need to be able to do that. Okay? Trying to give you fair warning. Just practice. This one you need to practice. You need to practice that one. Okay. D says find G of 2 over R. Again, we're doing the same thing. Negative 2 over R squared plus 4 times 2 over R minus 5. 2 over R squared is 4 over R squared, and there's a negative in front of it. 4 times 2 is 8 over R, and subtract 5. So that's G of R, 2 over R. That one's not nearly as hard as this one is.
Would you not multiply R by 4?
You multiplied it by R when you multiplied the numerator. Remember what you're doing here is you're multiplying 4 over 1 times 2 over R. So it's 4 times 2 and 1 times R. If you multiply both of them, then it would be this. It would be actually the same thing that you started out with, because the 4s would cancel. Okay? Now we need to tackle that last one. Find all the values of g of x such that g of x equals negative 12. What they're actually asking us to do there is to let g of x be negative 12 and find what value of x makes that happen. So this time you're substituting g of x with the negative 12. It has been a long time since any of you saw this. I know the last time you would have seen it probably would have been in Math 1100, maybe. And you would have done something called using the zero product principle. I don't know if you remember what that is, but basically you want to set this equal to 0. So if I add 12 to both sides, then this becomes 0 is equal to negative x squared plus 4x, and 12 minus 5 is 7. So it's plus 7. Now, there are two different ways to solve this. One of them is factoring. Everybody just loves factoring. Okay. So you can solve it by factoring. You can solve it by factoring. That will be fine. The negative x squared makes it a little challenging, but you can always flip all the signs around and use that. That has the same factors as this does. But the far easier way to do that, since I'm going to tell you up front that doesn't factor, is to use the quadratic formula. quadratic formula says take the opposite of b plus or minus the square root of the value of b squared minus 4 times a times c, all divided by 2 times a, and you'll get two answers, and both of those will work in that equation. So in that case, this tells us that a is equal to -1, and b is equal to +4, and c is equal to 28. So what our quadratic formula tells us then, 20, I don't know where my brain got that. Thank you.
I don't either.
I think somehow it looked at 4 and 7 and said, oh, 28. God knows why. C is equal to 7. So then if I plug all that in, my values of x are going to be the opposite of b, -4, plus or minus the square root of b squared, that would be 4 squared, minus 4 times a, which is -1, times c, which is 7, over 2 times a, and again a is -1. So x is going to be equal to -4 plus or minus the square root of all that stuff. 2 times -1 is -2. So that part's easy. We've got to get this part. So let's see. 4 squared is 16. -4 times -1 is 4. And +4 times 7 is 28. There's my 28. So 16 plus 28. Let's see, 16 plus 28 is 44. My math lab's going to make you do this, so I'm going to have to show you how to do it. I will show you how to check, make sure you did it right. And I will give you credit if you put in the decimals. I really will, because I don't see any point to your knowing how to do what I'm going to show you how to do. But I am going to show you how they got the answer. X is equal to, leave the -4 where it is, leave the -2 where it is. 44 contains a perfect square. The perfect square that it contains is 4. So they're going to take the square root of the perfect square part of it, and you're going to get that. And then because -2 will go into both the 4 and the -2 in the numerator, we're going to change this and say, okay, that's -4 minus 2 square root of 11 divided by -2, and -4 plus 2 square root of 11 divided by -2, and we're going to factor out -2 from both of the tops. Whoops. And when you've done that, then you can cancel out the -2's. So here's your two answers. No, this one should have been plus, because if I factored out the -2, that would have been +1. So that one's plus. One of them's plus, one's minus. Okay? That's what my math lab wants. Now, if I were doing it, And you can do it this way too. You're just going to have to click Ask My Instructor and say, what they've got in there is the exact same thing I've got. It's just that I went ahead and did it on the calculator. I'll give you credit for it. What you're going to do is go back up to the quadratic formula with your calculator. And you're going to say, first I'm going to do all the stuff under the square root because that's the hard part. So b is 4, so that's going to be 4 squared minus 4 times negative 1 times 7. Okay? So my answer is going to be negative 4 plus the square root of 44 divided by negative 2 and negative 4 minus the square root of 44 divided by negative 2. And so my answers are going to be negative 1.32 and positive 5.32. Close enough. Okay? Because if you actually evaluate 2 plus the square root of 11, and 2 minus the square root of 11, that's what you get. So I'm fine with the decimal answers because when we get to calculus next semester, we don't care about the answers with the square root signs in it. We care about an answer that we can make sense of in a problem. So if you want to just do this, the approximations and then just click the Ask My Instructor button and say, would you please give me credit, my answer's the same as theirs, and I'll do that for you. So you don't necessarily have to do all of this stuff here. You can just put it in the decimals. And the reason I'm saying that is because there's an easier way still to do that than what I showed you, and that's why we have a graphing calculator. And I think I actually put this in the PowerPoint, and then I'll show you on the calculator too. And because we're going to graph it, we'll determine the domain and range of this function as well, and find f of 3 and f of x is negative 12. So we're going to get the calculator. Go to your y equals. And I've already put it in there because we used it for something else to check. So what we're going to do then is we'll go ahead and graph this on a window from negative 10 to 10. Now I'm just going to let it fit with zoom 0, and then I'll adjust it from there. Okay, so I see that there's a lot of it down here and apparently not much up the top of it. So I'm going to go back to the window and go up. I don't really need to see down to a negative 145. We can go down to negative 50. And let's go up to about 5. So there's a graph of that function. And you can tell that the domain of that function goes from negative infinity to infinity because it's just going to keep on going down and out forever. The range, however, is at the very top of that graph. So I need to find the maximum value of that graph. So I go down to number 4 and I press enter, and I go to the left of it and press enter, and then I'll move my cursor over to the right of the top of that peak and press enter, and then I let it tell me where the top of it is. And it says its highest y value is negative 1. Okay? That's as high as it goes, is negative 1. So its range goes from negative infinity to negative 1. From bottom to top. Negative infinity is the bottom, negative 1's at the top. I can find f of 3 right there on the graph. Second, trace, choose value, and tell it, show me where x is equal to 3. This is, okay, there it is, y is negative 2. Okay? It would tell me the y value for any x I plugged in, as long as it's a number. And then it says, tell me where the x value is so that the f of x is negative 12. In other words, the y value is negative 12. What's the x value that gives me that? Well, what you do to do this last part is you go back to your y equals, and you let that function be negative 12. And then you hit your graph button. And that shows you there's two different x values that give you negative 12. One of them is right there. The other one's right there. And those are called intersection points. So you hit your second trace button again and go down and find your intersect button. And hit your enter. And what I like to do is get close to one of them before I start, because it'll find the one that I'm closest to. So I get it pretty close to the one on the left and hit enter 3 times. And it gives me the left intersection, which is, guess what? The same thing we got when we did all that work a few minutes ago. And the same thing and there's the 5.3166, which we said was about 5.32. Okay? Now, it's your choice. Would you rather learn to use it on the calculator or do all that? When I see you in January for 1830 for business calc, I would much rather that you know how to do that. That will be of more use to you in calculus than doing all that algebra. Okay? Let's see, this was the same thing. So, and that's a picture of that's in the PowerPoint. So I'm going to go back to the PowerPoint for a minute so we can finish up. We're almost done. We're going to talk about a vertical line test. A vertical line test will tell you whether or not a graph is a function without your having to do much of anything else, but just look at the graph. If the vertical line intersects the graph in more than one point, which we saw that once before already, that if you draw a vertical line on that graph and it touches it in more than one point, then that graph's not a function. This shows you that for this particular x value, there's 2 y values, this one and that one. So that graph is not a function. We looked at this graph a little while ago and we knew that any vertical line that we would draw on here would have crossed that graph in more than one place. So that is not a function. You don't get to get by, though, with telling me that the vertical line test says, because I want you to actually know how to explain why something is or isn't a function. So if I gave you this and said, tell me, is this a function? What I want you to do is draw a vertical line. I don't care which one. Draw a vertical line. That one would be fine. And say, For the x value 4, there are 2 y values, so this is not a function. Just pick one. And the reason I'm insisting upon that is because in the past, when I let people just tell me the vertical line test says it's not a function, they forget what a vertical line test is. And they try to draw a horizontal line, and it turns out telling them a lie, because horizontal lines don't test for functions, only vertical lines do. So be sure that you know what that vertical line test is really telling you. There's 2 y's for 1 x. Okay? Be able to explain it. And our last topic is something called even and odd functions. And this is one I'm pretty sure you've never heard before. And this will be on the final exam, so pay attention. There's actually 2 ways to tell even and odd, but I'm going to tell you neither one of them hard. A function is even if f of the opposite of x is the same as f of x. What that means is the graph is symmetric about the y-axis. Think about a parabola. F of negative 2 is the same as f of 2 on a parabola. That's that U-shaped function we just looked at. So the left side is a mirror image of the right side. The function is called an odd function if f of the opposite of x is the opposite of f of x. Now be careful of how you say that. The negative sign is read as the opposite of. So this one says f of the opposite of x is the same as f of x. This one says f of the opposite of x is the opposite of f of x. 2 different things. Now it goes on to explain that the graph is symmetric about the origin. Actually, the better way to say it is that if you flip it across the line y equals x, it looks just the same. But don't worry about what it looks like, because I'm going to give you a way to tell that makes it a little easier than that. What we'll do is we're going to go through 3 functions and determine whether each one of these is even, odd, or neither. So the first one we've got, we're just going to do a little bit of algebra here. All we really have to do any of these is plug in the opposite of x, or negative x, into what we've got. So what you do to determine if it's even, odd, or neither is you want to find f of the opposite of x. That means you plug in negative x everywhere you see x. What is negative x raised to the 4th power? Positive x, right? Positive x raised to the 4th power. Because negative times negative is positive, times negative goes back to negative, but then times the last negative makes it positive again. So that's x to the 4th minus negative x times negative x is positive x squared. And x to the 4th minus x squared is the original function. That tells you this function is even. That is an even function.
So if it comes up to be the original,
It's an even function. Okay, here we have f of x equals x over x squared plus 1. So we're going to plug in negative x. So negative x in both places. Negative x squared is x squared plus 1. Compare that to the original f of x. Are they the same? No, they're mostly the same. This one's negative, this one's positive. So that tells you that f of negative x is the opposite of f of x. They differ by a negative sign. That means this function is odd. Okay? So now we'll do the last one. F of negative x is negative x to the 4th power minus 4 times negative x to the 3rd power. Negative x to the 4th power is x to the 4th. Negative x to the 3rd power is negative x. Because if the power is odd and the base is negative, then your result is going to be negative as well, because you've got a negative times a negative times a negative. Okay?
Wouldn't the x to the 4th just be x by itself?
Well, negative x times negative x is x squared. Times negative x is negative x cubed, but then times another negative x is positive x to the 4th. It's still going to be x to the 4th power, it's just that your signs will pair up because of your even power. Okay? So x to the 4th minus 4 times negative x, which is x to the 4th plus 4, and let's see, that was negative x to the 3rd, so this would have been x to the 3rd. So that would have been x to the 4th plus 4x to the 3rd. Now compare that to your original function, which was x to the 4th minus 4x to the 3rd. Are they the same or are they opposite? Not completely. This is opposite. But what about the x to the 4th? It's only a half opposite. In order to be completely opposite, this would have had to be negative x to the 4th plus 4x to the 3rd. Okay? So it's not completely opposite. It's only partly opposite. So what that tells you then is that this one is neither even nor odd. Okay? If it's even, plug in the negative x and get back the original function. If it's odd, plug in the negative x, get back the opposite of the original function. But if you don't get either one, just something that's kind of similar but not exactly the same, then it's neither. Neither even nor odd. And there is one in the Shobi homework for you to practice, because that one you'll need to practice to be sure that you understand how to determine it. Okay? Last thing we're going to look at is something called delivery charges. And it's kind of a different, it's a sort of linear function, but it's only linear in places, I guess is the best way to say it. And these do come up quite a bit, and we look at these in calculus some, so that's why I wanted to leave this example in there. Overnight delivery service charges $25 for a package that weighs up to 2 pounds. X is the weight of the package, and Y is going to be what they charge. So if a package, now you obviously cannot have a package that weighs 0 pounds. Hope you agree with me on that. No package, no pounds, no charge. But if you have a package that weighs 1/10 of a pound, they're going to charge you $25. If it weighs 1/2 pound, they're going to charge you $25. If it weighs a pound, they're going to charge you $25. If it weighs 1.5 pounds, they're going to charge you $25. If it weighs 2 pounds, they're going to charge you $25. If it weighs 2 pounds and 1/10, they're going to charge you $25 plus 3. So they're going to charge you $28. If it weighs 2.5 pounds, they're still going to charge you $28. If it weighs 2.9 pounds, they're going to charge you $28. If it weighs 3 pounds, they're going to charge you $28. But as soon as it weighs 3 and a little bit, they're going to charge you $31. $3 more. All the way up until it weighs 4 pounds. They're still going to charge you $31. But as soon as it weighs even a fraction of an ounce more than 4 pounds, they're going to charge you $3 more. And they're going to keep on doing that. Now, I could push this a lot further, but I think you get the idea of where things are going. The only Y values are going to be 25, 28, 31, 34, 37, 40, and so forth. And there is going to be nothing connecting the graph between 25 and 28, or between 28 and 31, or between 31 and 34. So the graph is going to look a little bit odd. The graph looks like this. This is that first part of the graph where they charged $28. Until it weighed exactly 2 pounds, they charged $28. They didn't charge us for no package. That's why there's a little hole there. But as soon as it weighed a fraction of an ounce, they charged us $28. When it got to 2 pounds, as soon as it went even the tiniest fraction above 2 pounds, they charged us $3 more, which took us up to $28 or $31. Oh wait, I'm sorry, the first was $25. This is the $28. I forgot that there was no extra charge on the first 2 pounds. But as soon as it weighed anything more than 3 pounds, there goes $3 more. So that's going to be 28 plus $3 more is $31. So at the beginning, they don't charge us that $31, whatever. As soon as it moves, they do. And then when it moves from 4 pounds to anything more than 4 until it weighs 5 pounds, they charge us $3 more. So that's going to be 34. And then as soon as it weighs 5 pounds and a little bit more, it's going to cost us $37. And this would actually continue, but that's as far as we need to go. So you see why I said this function is linear in little chunks, but it's not a linear function. The name of this function is called a piecewise function. Okay? And for this one, it will be a little tough to write the equation for it. We're not going to worry about writing the equation. But the idea is that it changes behavior quickly. And even though it looks like right here it might not be a function, it really is, because it's defined as being, for example, here it's defined as being $25, not $28. And here it's defined as being $28, not $31. And here it's $31, not $34. Those little holes make a difference. So that's the last example that we're going to look at in this section. Okay? And I think you probably need a break because I think your brain's probably about fried. And section 10.2, we are not going to do much except use the calculator. So let's take a break till about 8:15, and then we'll come back and do quadratic functions. Give you your exams back. Okay, the kind of question that we're going to talk about in 10.2, we're talking about quadratic functions. A lot of this is going to be vocabulary. The rest of it's going to be calculator skills. We've already kind of went over some of it, so we won't have to do every single one. But if you need to know how much a company should charge for its seminars, when Power and Money charges $600 for a seminar on management techniques, it attracts 1,000 people. And for every $20 decrease in the fee, an additional 100 people would attend the seminar. And their managers are trying to figure out how much they should charge for the maximum revenue. That problem leads to something called a quadratic equation. And a quadratic function looks like this. Now there are other versions of a quadratic function that have parentheses and different letters with them, and you'll run across those. Those are called quadratic functions in vertex form. We're not going to worry about those. If you get one like that, put it in your calculator, graph it, and solve just like you do everything else. But the ones we're going to mostly look at are the ones that are ax squared plus by plus c. And a, b, and c all have to be real numbers, and a can't be 0. That's the basics right there. So this is a basic quadratic function. This basic quadratic function shows the value of a is equal to 1, and the value of b and c are all equal to 0 in this case. That graph is called a parabola. P-A-R-A-B-O-L-A, a parabola. Every quadratic function has a parabola as its graph. That means it is a sort of a U-shaped graph. It's not as flat on the bottom as the letter U is. It actually comes to a little bit more of a rounded oval-shaped point. But it does have a curve. It is definitely a curve on the bottom. The bottom of this graph, which in this case is at the origin, which is 0, 0, is called its vertex. The vertex is the minimum value on a parabola that opens up, and it's the maximum value on a parabola that opens down. If you folded this graph in half along the y-axis, it is symmetric with the y-axis. All quadratic functions are even functions. They will always be even functions. So a summary of the properties. The parabola opens up if A is positive. It opens down if A is negative. The y-intercept is always 0c. It's 0 and then the value of that last number that's added to the function. And we'll look at an example of that in a minute. The x-intercepts, if they exist, will occur where the function value is 0. Or in other words, where the y value is 0 and therefore that's going to be points on the x-axis. The vertex is easy to find because it's always minus b over 2a. Although you could use your calculator to find it as well. But the formula for the x value of the vertex is minus b over 2a. You don't have to graph it. And then you plug what you get in for minus b over 2a into the function, and it'll give you the y value for the vertex. And the axis of symmetry always contains the vertex, and it's always a vertical line. So its axis of symmetry is always minus b over 2a. So here's our first quadratic formula. And we're going to graph this quadratic function, but first we're going to find some information about it that we're going to need to know. So in this particular situation, we have x squared minus 4, which means in proper notation, this is 1x squared plus 0x, because there is no middle term, minus 4. And that tells us that a is equal to 1, b is equal to 0, and c is equal to negative 4. The fact that a is equal to 1 tells us that it opens upward, which means its vertex is going to be a minimum. We know that its y-intercept, because the value of c is negative 4, its y-intercept is 0, negative 4. We know that its axis of symmetry, which I abbreviate with AOS, the axis of symmetry, is the line x equals minus b, which is 0, over 2 times a, which is 2 times 1. So the x value over the axis of symmetry is x equals 0, which means it's the y-axis. Because the equation of the y-axis is x equals 0. And then if we want to find its x-intercepts, we can find them algebraically by taking x squared minus 4, setting it equal to 0, and either using the quadratic formula or factor and use the zero product principle and find out what x values cause y to be 0. And since this factors into x plus 2 and x minus 2, then either x plus 2 is equal to 0 or x minus 2 is equal to 0, or both, which means that x is either negative 2 or x is equal to positive 2. So that tells you your x-intercepts are negative 2, 0 and positive 2, 0. And that's all the information that you actually need to be able to sketch a quick graph of that function. You know your axis of symmetry is your y-axis there. You know that negative 2, 0, and positive 2, 0 are going to be your x-intercepts, and you know that your y-intercept is at negative 1, 2, 3, 4. Now, you could use your calculator to get a few more points to make drawing it a little bit easier. So going back to my table, I'm going to choose a few numbers from negative 3 to positive 3. I already have negative 2, so I'll use negative 1. I already have the value of 0, so I'll use positive 1 and 3. And I see that at negative 3, the value is 5. So 1, 2, 3, 4, 5. And at positive 3, I'm going to be at 1, 2, 3, 4, 5. And at negative 1, I'm at negative 3. And at positive 1, I'm also at negative 3. And then I just need to connect these up with a nice smooth curve. Do not make it come to a point at the bottom. Make sure it's rounded. So that's a nice graph of f of x is equal to x squared minus 4. And that's all there is to it. And that's with doing all the algebra work that you need to do. And then if you need to, you can always verify on your calculator. And that is what it looks like. Okay? Any questions? Let's try a different function. This one says graph negative 4x squared minus 8x plus 5. Now I'm going to go through some of the same steps. A is equal to negative 4. B is equal to negative 8. C is equal to 5. This tells me that my parabola opens down because it's negative. This tells me that my y-intercept is 0, 5. I know the axis of symmetry is x equals minus b is negative 8 over 2 times a, which is negative 4. So negative 8 is positive 8 over negative 8. That tells me that x equals negative 1 is the axis of symmetry. And that's a vertical line. And I'll know the vertex by plugging in negative 1 into the original function. Although the easier way to do it would be to come over here and put it in my calculator, since I know it does arithmetic better than I do. I'll delete out all the ones that are there. So I want to know what is the value, the y value for the vertex, and that's where x is -1. So the vertex is at -1, 9. And then I could get some more points from using the table too. But I also need to know what the x-intercepts are. Now, looking at this, I don't even want to talk about factoring that. Maybe it factors, maybe it doesn't. If I were going to do that algebraically, I'd use the quadratic formula. And since I know this is the hardest part, I'm going to calculate it over here. So I know -8 squared is 64. Negative times negative is positive. 4 times 4 is 16, and 16 times 5 is 80. And that's 144. So the value of this part's going to be 144 over 2 times -4. So then x is going to be 8 plus 12 and 8 minus 12 for the top part, because the square root of 144 is 12. And then 2 times -4 is -8. 8 plus 12 is 20 divided by -8, and 8 minus 12 is -4 divided by -8. So that's going to be 1/2. And that's going to be 5/2, which is 2.5. It should be -5/2. So that tells me then that my x-intercepts, some more points on my graph, are -2.5, 0, and 1/2, 0. And I can also find those on the calculator. But in order to check all of this, since these are relatively nice values to plug in, I can verify on the table. So -2.5, and I get 0, and 0.5, and I get 0, so that verifies those are my x-intercepts. So I'm ready to graph and then check with my calculator. So where did I put the graph paper? And since I know that I'm going to have to graph 1/2, I'm going to scale this by 2s. So this is 1, 2, 3, 4, 5, -1, -2, -3, -4. And then now just because I scale this by 2s doesn't mean I have to scale the y-axis by 2s. I can leave it by 1s. So unless the vertex gives me a reason not to do that, I'm going to look and let's see, the vertex is -1, 9. So no, I think I'm going to scale that by 1s. So this is going to be 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. negative 1, negative 2, negative 3, negative 4, negative 5, negative 6, negative 7, negative 8, negative 9, negative 10. I know that my x-intercepts are negative 2.5 and 0.5. I know that my vertex was at negative 1,9. That tells me that my axis of symmetry is,
Supposed to be negative 1.
Is it? negative 1, oh, positive 9, thank you. Ah, let's go up here. Thank you for catching that. So, and it's opening down, so that makes sense. And then 0, negative 5 is my y-intercept. And by symmetry, since I know that from the axis over this way, 1 unit gives me a point, then if I go to the axis and go the same distance, that gives me another point because of it being
Should it be
symmetric.
0, positive 5?
Yes. Thank goodness y'all are awake. I keep trying to turn that parabola right side up. So this is at negative 2, 5. And I've got plenty now to actually sketch the parabola. So there's a graph of negative x to the 4th I'm sorry, negative 4x squared. I can't even talk now. Maybe it's time to quit. So there's your graph. Now, other than the teacher messing up, do you have any questions?
Will you be doing this for the classes?
Yes.
And she'll be posting video?
Yes.
for us?
I'm recording this one too, so I'll post both. I usually do post both. Now, since I want to be sure that we get to the graphing calculator part of this, and I think I only have one example left in this, I'm going to show you how to do this one almost completely on the calculator. So what we're going to do on this one is we're going to go to the calculator, and I'm going to use the table to help us with the actual graph, so I'm going to wipe out what's in the table. Change the function to x squared plus 4x plus 6. And then we're going to go ahead and hit, let's see, check the window, negative 5 to 5. Maybe let's go negative 10 to 10, just in case. So this is your standard window. Let's just hit graph and see what we see. Could you have predicted that it opened up? Because the value of A is 1. We know also that its y-intercept should have been at 0, 6. So that makes sense. Does it have a vertex? Yes, they all do. Its vertex is right there. Now we can find it using the minus b over 2a. That's where x is equal to negative 2. And then negative 2 squared plus 4 times negative 2 plus 6 is going to be 4 minus 8 plus 6, which is going to be positive 2. So the vertex is at negative 2, 2. And the graph shows us that it's at negative 2, 2. And we can also hit second trace. And since it's a minimum, go to minimum. Move to the left of it, hit enter. Move to the right of it, hit enter. Enter one more time for it to tell us where it is, and the calculator verifies almost that it's negative 2, 2. The calculator doesn't actually do the quadratic formula. The calculator does a little thing called numerical analysis. It goes from the first number to the second number and says, okay, I'm not getting a sign change, they're both positive. So then it moves closer and closer and closer and closer and closer until it sees that there's no difference, no discernible difference in the answers. Then it says, oh, well, that must be the answer then. It's x equals 1.99999. Well, no, it's 2. It's actually negative 2. There are no x-intercepts. The graph told you that immediately. The reason I chose to show you the graph is because if we try to do the quadratic formula with this, because it doesn't factor, by the way. If you do the quadratic formula, x equals minus 4 plus or minus the square root of 4 squared minus 4 times 1 times 6 over 2 times 1. 4 squared is 16, and 4 times 6 is 24. 16 minus 24 is negative 8. And we have a problem. You can't take the square root of negative 8. If you try to do it on your calculator, it tells you exactly what the problem is. Non-real answer. It is not a real number. Okay? So if x is not a real number, that tells you it's not a number that you can plot on a graph, so it has no x-intercepts. And if you ever need to figure out, without your graphing calculator, if there is a real answer or not, you actually only need to worry about this part, because that's what's going to tell you. So if you evaluate b squared minus 4ac, and it turns out to be negative, there are going to be no x-intercepts. And then you should be able to verify that using your calculator. So that's everything that we know to actually be able to graph that. And if you wanted to graph it onto paper, whoops, all you would need to do, since we've got it in the calculator already, is just hop over to your table and ask it for some x values. So we could ask it for negative 4, negative 3, negative 2, negative 1, 0, 1, 2, oops, messed up, 0, 1, 2, 3. And we would have more than enough points. In fact, we don't even need the 327 to be able to graph it. We could just use the 2. And even 2 probably won't fit on most graphs. So you use your table to get your points to graph it. Okay? This is that problem that we looked at the very beginning. In order to solve the problem, what we're going to do is we're going to let, since it seems to increase by $20 for every additional 100 people, we're going to let X be the number of $20 increases. And that means that the price per person is going to be $600 when it attracts 1,000 people, minus $20 for every time they decrease the price. And then the number of people is going to be that 1,000 people and then for every increase in price, which remember that's X, that's going to get another 100 people. So that's 100 plus X. And what we need to find is their revenue. And the revenue is how much per person times how many people. So that will be what we call the revenue equation, R of X. Now you can simplify that. We can actually multiply that out, and I would encourage you to actually do that. But given the form that it's in, where are they going to find their maximum revenue? The first thing you know about this is that when you multiply that term times that term, you're going to get an X squared, which means this is going to be a parabola. And because that's negative and that's positive, that's going to be a negative X squared term. So that parabola, oops, may as well close that, we don't need it. So that parabola is going to open down, right? So what we know about that parabola is that we're looking for its vertex. Now, if you want to try to find the vertex on the calculator, use this just exactly like it is. If you want to find the vertex without using the calculator, you multiply all this out. So 600 times 1,000 is 600,000. Minus 120,000x plus 600,000x is going to be turn out to be 40,000x. And then negative 20 times 100 is negative 2,000 x squared. And because you know a formula and all you're interested in is the vertex, you really don't care about anything else, then we can find the vertex pretty easily at this point. Need a little bit more room though. So I'm going to rearrange it so the x squared comes first, and I know what a is. Negative 2,000 x squared plus 40,000 x plus 600,000. This is A, that's B, that's C. X equals minus B over 2A. x equals 10. And then r of 10 time to break out the calculator. In fact, I'm going to make this really easy because I'm going to try to graph this when we're done, once we have an idea of where the vertex is. So $800,000. So that's the maximum revenue. And if you need to know how many people produce that maximum revenue, it's 2,000 people. Because that's your people equation. And the price per person is $400 a person. Okay? So there's your business application. And I think that's the only problem we have. If it's not, I'll finish up later. Now there is one about profit, but it'll be on the other recording because I don't want to take the time to do the profit. We're down to about 5 minutes. So, need to give you your test back.